Hello, students. Welcome back. Dr. DA here, and this is the second in a set of 3 lectures that you are studying on your own before we proceed into the next unit, which is unit number 9, the Lewis theory of covalent bonding. In the first set, we talked about the shapes of orbitals and how to uh, come up with the electron configuration for an atom if we know the numbers of electrons, and we have a diagram or a electron configuration to fill in sub-level by sub-level, right? In this lecture, we're going to talk about the relationship between the periodic table and this particular model that we're studying, the quantum model of the atom, all right? So if you can go to your PowerPoint notes and follow along, let's talk about this for a moment here. Okay, uh, the first thing that comes up is patterns. You know, periodic table, when you say periodic, it means there's some repeating patterns in here, right? So that is what we're gonna be talking about here for a moment. And let me pick up some stuff that I need here. Just give me a moment. I'm sorry about that interruption. I had somebody at the door here. Just a moment. We are back, right? Okay, let's go back to our PowerPoint again. Sorry. And let's consider the following. Let's say that I were doing the electron configurations. Now, last time we did the first 10 elements. Let's say that you were to do the whole thing for the whole periodic table. Of course, you would want to use the abbreviated one, right, where you put in a noble gas core, or kind of like prefabricated shell. And then on top of that, you add the extra electrons that that particular atom would have. And you come up with a table that looks like this. So it's kind of small and blurry, but I just want to point out a few things. Look at hydrogen. You said it was 1s1, correct? Let's look at lithium, which is the next element in that same group. And you notice that it ends up at 2s1 with a core of helium. The next one down would be sodium, right? Sodium is a core of neon, and then it's 3s1. And the next will be potassium, core of argon, 4s1. So you can see the pattern here that all these elements that are in group 1a, all of them have one electron in their outermost subshell. Not only that, but that outermost subshell is actually an s orbital. Let's look at the other side of the periodic table. Let's look at, let's say, fluorine. Core of helium, 2s2, 2p5. If you look at the next element down that group, which would be chlorine, you can see that it is 3s2, core of neon, 3s2, 3p5. And unfortunately, this table kind of skipped bromine, but I'm going to put iodine in here. You can see him there where, again, it's a core of krypton. It has a few electrons in the 4d subshell, and then it ends up again in 5p5. So notice several things about these elements. First of all, in their outermost, or the last subshell that is filled with electrons, all of them have exactly 5 electrons. Not only that, but the outermost shell being occupied for fluorine, it's 2, for chlorine, it's 3, for iodine, it is 5. In other words, it corresponds to actually the period that these elements are in the periodic table. The third thing you can notice is that if you add the total number of electrons in that outermost shell, so before, for hydrogen, lithium, sodium, potassium, it was 1, and they are in group 1a. For fluorine, chlorine, and iodine, you have 5 plus 2, that's 7, and they are in group 7a. So you can start seeing how the electron configuration connects with the placement of these elements on the periodic table. As a matter of fact, if I were to map out the periodic table and look at what is the outermost subshell that's being filled, we're going to get at this thing here. Notice this. Notice that the elements in groups 1 and 2, they all end up being filled at an S subshell. The elements on the right side of the table all end up being filled at a P subshell. And the transition metals all end up being filled towards the D subshells. And then we have the lanthanides and actinides, which are in F shells. Not only that, but the outermost subshell being filled corresponds to actually the number of the period. And we're going to call that the valence shell or the valence level. This is essentially what is the highest energy occupied level or shell. And you can see the pattern along there, all right? So with this in mind, let's rebuild the periodic table. But now let's put in boxes that correspond to what these, outermost subshells are. In other words, the valence shells. And we can look and see the diagram on the top. If I start with 1s, which would be hydrogen, and I go to the next element, which is 2s, and then I start a left to right and zigzag back to the left and left to right and zigzag back to the left and left to right, you can see that as I cross in here, it gives me the actual sequence of orbitals. So let's look at the top here. 1s would go to 2s, would then come to the right to 2p, which would then go back here to 3s. Then it comes back here, and notice that it comes into 3p, and then it zigzags back to 4s. And notice that the next one that it hits is actually 3d before going to the actual 4p. And this is exactly the pattern that we saw when we were doing the Aufbau diagrams. So you don't need an Aufbau diagram. You simply need to have the periodic table. And if you want, you can color in the different blocks, the S, the D, the P block, the S here being in green, if you can see the color, the D block being some kind of like a beige color, and the P block being in a kind of light blue color. All right, let's look at just the first 3 periods in here, just for illustration. And what I've done here is I've placed the elements that fall into that S and that P block. We're not going to consider the transition metals for now. Notice that on the top, we've put the numbering of the groups according to what I called the, I guess the American way of numbering them. Instead of numbering them sequentially from 1 to 18, we go 1A, 2A, then we skip the transition metals and pick it up in 3A, 4, 5, 6, 7, 8A, which is the noble gases. Look at the electron configurations underneath each one of these, and you'll notice, number 1, that the valence shell, in other words, the highest occupied level, the value of N corresponds to the period. So look at period 3. All of the elements in period 3, their valence shell is level 3. Not only that, but if you count the numbers of electrons you have in that valence shell, you'll notice that it corresponds to the number of the group. So let's take, for example, nitrogen and phosphorus. 2s2, 2p3, 3s2, 3p3, respectively. You add those up and you get 5, which is actually the group number. And so based on a position on the periodic table and knowing this quantum model, you can now essentially predict what is going to be the configuration of that element in its valence shell. How many electrons are in there and which subshells are occupied, all right? Now here's another thing. Let's look at the left side there. How many columns are in that S block? 2, right? Let's count the number of columns in the P block, starting, let's say, from boron through neon. 1, 2, 3, 4, 5, 6. So ask yourself, how many electrons can you fit in an s orbital? 2, right? How many electrons can you fit in the p subshell? 3 orbitals, 2 electrons each, that's 6. In other words, the number of columns in each one of these blocks is the same as the number of electrons allowed in each subshell. That means that if I want to write the electron configuration of an element or an atom, I don't really need the orbital diagram. All I need is the periodic table. Let me do one practice for you, and then I'm going to let you guys do a couple on your own, okay? So let's look at the electron configuration for chlorine. All right, and this might not be in your handout. I think I might have forgotten to include it in your handout, right? Okay, so there's chlorine. Okay, the first thing you notice is, let's put it in the periodic table right there. Okay, let's start out with what its core configuration is. That would be the previous noble gas, which is neon. So that's going to be my core. So I'm going to start my configuration with the bracketed, symbol of neon. And now I'm going to go to the next period here, and I'm going to go from left to right. And I'm going to count the number of columns, okay? So notice that in the S block, there are 2 columns. So that's 2 electrons. And if I go back here to where chlorine is, starting with column 3A, I have 1, 2, 3, 4, 5. In other words, the chlorine is in the 5th column. That means 5 electrons. So I can write out the configuration by putting in the core of neon, 3s2, 3p5. I don't know, it's 3. Well, because chlorine is in period 3. See, very easy. You don't even need to have an orbital diagram for this. All right. Okay, let's do some practice for yourself. I want to give you a few moments to practice these guys here. All right. Phosphorus and manganese. Again, remember, choose who is the core noble gas, and that's the bracketed form of your abbreviated configuration. And then in the period where the element is, start out by writing out the number of columns. Don't forget that when you hit the D subshells, your actual value of n drops, because remember that because of that zigzag pattern, after you hit 4s, the next set of orbitals are going to be, the next subshell is going to be 3d, not 4p, not 4d. Okay, so let me give you a few moments. Just count the columns and see if you get these answers. For phosphorus, right? Neon, 1, 2, that's 3s2, 3p1, 2, 3. There you go. How about manganese? Core is argon, and then you have 4s1, 4s2, and then comes the 3d ones, 3d1, 2, 3, 4, 5. So that means that our configuration is core of argon, 4s2, 3d5. See how easy it is? I told you guys last time that there was an easier way than writing all those diagrams, right? Okay, so at this point, let's make a quick review. Okay, oh, I forgot to show you these things. So you might want to have this chart in here to show you the progression. This is where you could see that from 4s, you go through 3d before you hit 4p. Sorry, I forgot to put that up there. Okay, so let's review here. Each value of n is a shell, and there's going to be n subshells in it. In other words, n values of L. The values of L go from 0 to n minus 1, so L can never be equal to n. And each subshell contains 2L plus 1 orbitals, in other words, 2L plus 1 values of ML, with ML going from minus L to plus L. You cannot have more than 2 electrons per orbital. So therefore, the total number of electrons, the maximum number of electrons would be 2 times the number of orbitals that are available to that particular atom. Remember that some atoms, because of the period they're in, they cannot go above a certain value of n anyway. Maximum number of electrons in one shell would be 2n squared. And again, these are kind of like calculations. You don't have to memorize these things. But if you want to, that's fine. Be my guest. All right. The other thing we found is that when we combine our knowledge of the quantum model with the periodic table, we find that elements can be grouped in blocks based on what is their highest partially occupied subshell. So you have the S, the P, the D, and the F block. We found that the length of each block, in other words, the number of columns, equals the maximum number of electrons a sublevel can hold. So in other words, whatever column in a block an element is, that is actually the number of electrons that element has in that block. The period number corresponds to the principal energy level of the valence electrons. Remember that for a D block element, transition element, that valence level is actually going to be typically an S, a sublevel, not the D electrons that are in there. And we'll see more about that later on. Lastly, the group number, 1A, 2A, 3A, 4A, corresponds to the number of valence electrons. This only applies to those elements that belong to the S and the P blocks. Remember, the D block elements are a little different. So again, we can look again here at the, at this periodic table. I don't know if you can see the colors very well, they're kind of faint, but on the left side, we have the 2 columns of the S block in kind of light blue. To the right side, we have the 6 columns of the P block in kind of like a light, faint purple there. And then in the middle, we have 10 columns for the transition metals or the D block elements. And again, remember, there are 5 d orbitals. That means 10 electrons, therefore 10 columns in this block. And then inserted in there, but taken out for the bottom, are the F block elements. These are the lanthanides and the actinides. All right. Now, one of the things we learned before was that many elements, when they form compounds, or the way they're found in nature, is not as the neutral atoms, but as ions. So let's see what happens when we make ions and we represent them using these electron configurations. Okay, so here's sodium, right? Core of neon, 3s1. What would be the ion of sodium? Well, it'd be 1 electron less. And notice that, as we mentioned back in chapters 2 and 3, I believe it's chapter 3, the sodium ion mimics neon, but now we can see that it's not simply the number of electrons. Back then we said, well, sodium with 11 electrons would rather have 10 like neon. Notice that now we have a little more detail. What we see is that the sodium ion is built like a core of electrons of neon, which we said is a full set of subshells, right? Let's look at calcium. Core of argon, 4s2. We know calcium makes a +2 ion. Notice that the calcium ion would essentially be a core of electrons like argon. Let's look at aluminum. Core of neon, 3s2, 3p1, and we know aluminum makes a +3 ion, right? Before we said, well, it's because it wants to have 10 electrons like neon. But notice that it's more than that. It's more like it wants to have the electron configuration of neon, which, because it represents full shells, it's more stable. So essentially what we're saying is that atoms lose electrons, particularly metals, so that the corresponding cation has a noble gas outer electron configuration. Now let's look at the ones that make anions. I'm going to skip hydrogen because we don't talk about the hydride ion that much. Let's look at fluorine. 1s2, 2s2, 2p5. We said that fluorine gains an electron, and if you can see, that would give it the same configuration as the noble gas neon. Again, remember, these are electron configurations. These are not atoms. Okay, the nucleus hasn't changed. Fluorine still has the 9 protons. Let's look at oxygen. 1s2, 2s2, 2p4. We said that oxygen gains 2 electrons. That will give it the same configuration as neon. Let's look at nitrogen. 1s2, 2s2, 2p3. And we said that it gains 3 electrons. Well, the only place for those is that 2p subshell. So the nitride ion with a -3 charge would have the same electron configuration as neon. In other words, atoms, particularly nonmetals, will gain electrons so that the anion has a noble gas outer electron configuration. Here's the important thing though. All of these losses or gains of electrons are happening with electrons of the valence level. The core electrons are not being changed here. And so when we look at these so-called, the S and the P block elements, which are sometimes called the representative or main group elements, you can see where, because of what we just talked about, the group 1 elements will form a +1 ion, group 2A will form a +2. The, the non-metals here in, the metals, in group 3A will form a +3. And then the non-metals, again, -1 for group 7A, -2 for group 6A, and -3 for group 5A. Of course, that applies only to those elements in that group that are non-metals, all right? I know the arrow is pointing all the way down, but realize that some of those elements there are below that zigzag separation line that divides between the non-metals and the metals. Now, I think as we were looking at those configurations, I think you picked up something. For example, the sodium ion is essentially the electron configuration of neon. So is the aluminum ion, and so is the fluoride ion, and so is the oxide ion, and so is the nitride ion. Notice that all of these species, even though they have different nuclei and they have different charges, their actual electron configuration is the same. So the word we have for that is, we would say that all of these species are isoelectronic with neon, or let's say simply isoelectronic, which simply means they have the same numbers of electrons total, same numbers of electrons total. They have the same outer configuration. So let's practice here a little bit. If I were to build the potassium ion configuration, what would be the neutral atom that is isoelectronic with it? All right. So very quickly, locate your periodic table. Find out where potassium is, right? It should be essentially a core of argon with one more electron in 4s. Or if we expand it, it'll be like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. We know that the potassium ion is missing one electron. Well, the one that is going to drop is that one in the outermost level. And that gives us a configuration that is the same as the electron configuration of argon. So the answer is that potassium ion would be isoelectronic with argon. Okay, every story has its little nuances, every pattern has its exceptions. And of course, here we go. Who are the exceptions? Transition metals. So essentially, the way we define a transition metal is we say that it's an element that has an incompletely filled d subshell, or it gives rise to cations that have incompletely filled d subshells. And what we find is that as we go through those elements, we're going to find some irregularities in the building up pattern. In other words, that trick that I showed you about essentially scanning to the periodic table and counting columns and getting electrons, it doesn't work for all the transition elements. All right, let me come up here. I'm going to show you something here just so you can see what I mean. Let me come back here to our Hope you're seeing this here, our little makeshift whiteboard. Okay, I'm going to use line paper because I have to draw some straight lines, and hopefully this won't be kind of weird here. Okay, let's consider the element vanadium. And by the way, let's do this. Let's go to our periodic table here for a moment. Okay, where's vanadium? There it is. It's atomic number 23. And notice that if you go here, you have a core of argon, and then you have potassium, calcium, so that'd be period 4. So 4s1, 4s2, right? Right? And then 3d1, 3d2, 3d3. Okay, so let's do this. Let's go to our table here, and let's draw these things out, okay? So let's say vanadium is 4s2, 3d3. And of course, we have a core of argon. So let's pretend I'm going to draw these things here. Let's say this is okay, argon here, core. And then I have, this would be the 4s subshell. And then we go to 3d. And remember, there's 5 possible orbitals in there. And I had to put 2 electrons in 4s. So I'm going to put them with opposite spins. And then 3 electrons in 3d. According to Hund's rule that we talked about last time, they need to be, as long as possible, they need to be in separate orbitals. So that is the configuration that we would do for vanadium, all right? Well, let's look at the next element, chromium. So chromium has 1 more electron, so we would say it's 4s2, right? Core of argon again, 3d4, right? In other words, if I draw the configuration here, 1, 2, 3, 4, 5, or rather, let's call this the electron diagram or the Aufbau diagram. Here's 4s, and again, we have a core of argon. So again, I'm going to put 2 electrons in 4s, 4 in 3d, but since I have 5 orbitals available, I can keep those 4 electrons in separate orbitals. Now, one of the things that we find is that I mentioned this at the end of the previous lecture. There's an experiment you can do where you can test for whether a particular species is paramagnetic or diamagnetic. Paramagnetic means that there are unpaired electrons. In other words, there are electrons that have a spin that is not counterbalanced by one other opposite spin. Notice that this predicts that there are 1, 2, 3, 4 unpaired electrons. Here's the problem. The study tells us that there are actually 6 unpaired electrons. Now remember, theories are good and models are good, but only if they are corroborated by data. So here's the proposal, and here's what was found. The actual, so in other words, this doesn't work. Let's try it again. 1, 2, 3, 4, 5. 4s, core of argon. All right, let me pull this over here a little bit. There you go. The only way you can do that is if you leave the 4s orbital only partially occupied, and you put 5 electrons, each in one of the 3D orbitals. And it turns out that this is the actual configuration. In other words, core of argon, 4s1, 3d5. Why is that? Well, here between you and me, it takes a little bit of hand waving, mainly because we don't have the math here with us to kind of calculate these things out. But for reasons beyond the scope of our discussion, let's say that this arrangement where you have all of these 6 unpaired electrons out there, and each orbital of the 3D subshell having 1 electron apparently is a lot more stable than the other arrangement that we would have predicted. Like I said, the atoms in the transition metals region of the table, they don't always follow the predicted patterns, all right? So coming back here to our PowerPoint, let's go ahead and talk about that. I think it has here the summary. For example, chromium, we said, is argon 4s1 3d5 instead of 4s2 3d4. Copper is the same. Instead of being 4s2 3d9, it's 4s1 3d10. So for whatever reason, these 3d5 and 3d10 configurations are more stable than their corresponding predicted ones, all right? So that's an interesting thing. The other thing that's interesting is the ions that are formed by transition metals. So it turns out that when you look at the configuration of a transition metal and they form cations, the electrons that are removed are first removed from the corresponding S subshell, not from the D subshell. Let's look at an example. Here is the configuration for iron. Core of argon, 4s2, 3d6. Again, if you want to go back, let's go back to our periodic table so we can find it here. Okay, so here's iron, right? Here's iron. There we go. And atomic number 26. So again, it'll be argon, 4s1, 4s2, 3d1, 3d2, 3, 4, 5, 6. There's no exceptions in this case. So coming back here to our discussion, let's go back to our screen. And let's say that basically that is the configuration of iron. Now we learned that iron can make 2 different kinds of ions, the iron 2 and the iron 3. Well, let's see what that looks like. Instead of taking out the electrons from the 3D subshell, iron 2 is made by taking out the 2 electrons in the 4s subshell. And so what is left is a core of argon 3d6. Think about it. Technically, the 4s subshell is farther away from the nucleus than the 3D subshell. So it kind of makes sense that anything that's going to take electrons away would find those electrons first because they'll be the outermost ones. Now, what about the iron 3? Now, to make the iron 3, you now take an electron off of that 3D subshell. And notice what we find. We find a core of argon with a 3D5, which, as we said before, is a fairly stable configuration. You have 1 electron in each of the 5 orbitals that are available in that subshell. So let's look at manganese. So manganese, core of argon, 4s2, 3d5, right? Very stable thing. Interestingly, when you make the manganese 2, you take out the electrons not from 3d but from 4s, and you end up with a configuration that's argon 3d5. Notice that manganese 2 would be isoelectronic with iron 2. So you can see here, right? See that? So argon 3d5 would be isoelectronic with iron 3. Now, when you make the manganese 3 ion, of course, you would take one of those 3D electrons, which is not very easy, and therefore not as common, not as stable an ion. So a couple of things come up here. First of all, we find that the electrons might not be removed in the same order they were added when building up the electronic configuration. So if we were to build, let's say, iron from the bottom up using an Aufbau diagram, and now we're going to take out electrons, notice that we don't take them out in the reverse order of how they were built up. The other thing we find is that the cations are not always isoelectronic with noble gases. Notice that neither the iron 2, nor the iron 3, nor the manganese 2 ions are isoelectronic with a noble gas. They have a core of a noble gas, but then they have some electrons in the 3D subshell. All right? Okay, so that concludes this portion of our lecture. Our next topic is, now that we have the connection between quantum models and the positions of elements on the periodic table, now we're going to be able to analyze the periodic properties of elements. Okay, so please stand by for the next lecture where we'll discuss that topic. Thank you so much. I'll see you soon.